Welcome everyone. For today's prep, we're going to look at our last topic here, and that is the area in between two curves. So we've already seen how we can use the definite integral to help us calculate the area underneath one curve. Well, now we're going to be looking at the region that's sandwiched in between two curves. So first, let's get our formula here, but let's actually go down and look at kind of the scenario, a little bit of a picture for what we're going to be doing. So we're going to have one function f of x, and this is the one that is higher up on our page. So when we're talking about this, I'm going to call f of x the top function. And then we have a second function, g of x, and this one is lower on the page. So I'm going to usually refer to this one as the bottom function. So we've got our top function and our bottom function. And what we want to do is we want to calculate this area going from, we've got our vertical line at x equals a on the left, and then our vertical line at x equals b on the right, and we want to find the area for this region here. So this is the area in between. So how are we going to calculate that? Well, the idea is we're going to first calculate the area under f. So we're going to forget about function g temporarily, and we're just going to look at this region that sits completely underneath f. So there we go. We're going to figure out the area underneath f. And the idea is we're going to cut away. So we're going to remove or subtract the area that also sits underneath g of x. So imagine if you had a piece of paper here. Imagine if you had a piece of paper, and all we're going to do is we're just going to cut along, we're going to cut along the line g of x, and we're going to remove that section here. So that's all we're doing. We're going to figure out the total area underneath function f, and then we're going to cut away that region that sits underneath g, and we're just going to remove it. So imagine you're just cutting some paper here. And what we have left then is this region that's underneath f, but above g of x. So it sits in between the two. So we know how to figure out the area under f of x. This is precisely the integral from a to b of f of x. And we also know how to figure out the area underneath g of x. So this is just our definite integral. So we have minus the integral from a to b of g of x. Well, we have one of our integral properties that says when we have a minus sign in between two integrals like this, we can just combine them into one. And so the area in between, another way to calculate this is instead calculate the integral of our top function minus our bottom function. So just put those two integrals together. And that's the idea. That's what we're going to be doing. We're just going to subtract our two functions and calculate our definite integral. Now, when we do this, there is one thing we have to be careful of. So when we set up this formula to calculate the area in between two curves, we want the function we put first to be our top function. And then we want the function that we put second to be the one that's lower on the page. So we want this to be our bottom function. And the reason why the order matters here is because we have this subtraction sign in the middle. So we're taking the higher up function and we're removing the bottom function. All right, so with that in mind, let's try an example. So we have these two curves, y equals 2x squared minus 4x plus 6, and y equals negative x squared plus 2x plus 1. And we want to find the area of the region in between these two curves going from x equals 1 to x equals 2. So in the graph here, we've got the graph of the two functions. So you can see nice picture here of our two functions. And we're going from x equals 1 to x equals 2. And we're just looking at that region that sits in between the two of them. So what we have to do is we have to figure out which of these is the top function and which one is the bottom function. And one thing we're going to have to do in general, first thing, is just think about if there's any intersection points between the two curves. Now, looking at this one, no. Each of these is a parabola. One of them opens upward, the other one opens downward, and I don't see any points where these two curves are going to intersect. So right now, we're just going to say for this, there's no intersection points. We're going to try an example where we actually have to figure out the intersection points. So for this one, though, there are none. These two curves don't intersect. So once we have that all figured out, then we have to figure out which is the top function and which is the bottom function. So to do this, we're going to do just a tiny little sign chart. So we're interested in this interval going from 1 to 2. So we have our two endpoints here. We don't have any intersection points to plot. So if these functions were labeled, then we could just probably figure out whichever curve this is, that's going to be our top function. But let's suppose we didn't know which curve this is. And this one's not labeled. So how could we verify this? Well, one way to do so is with a test number. So there's no intersection points here. So we can pick any point in this interval here. So let's take x equals 1. And the idea is we're going to take that test number and we're just going to plug it in to each of these functions and see which one gives us the largest value. All right, so let's plug it into the y equals 2x squared minus 4x function. So 2x, and again, we're plugging 1 in, so we get 2 times 1 squared minus 4 times 1 plus 6. And if we simplify that, we end up with 2 minus 4 plus 6. So that is 4. Yep. Now, what about if we plug that into the other function? Well, we end up with negative 1 squared plus 2 times 1 plus 1. And if we square the 1 first, we get positive 1. But then we have this negative in front, so this is negative 1. And that ends up being 2. So what this is telling us is our top function is whichever number was bigger. I'm going to use, maybe I'll use blue and green. So 4 here is the bigger number. So whichever function we plugged in to get that number, that's the top function. So in order to get this 4, we were plugging into the 2x squared function here. So our 2x squared minus 4x plus 6, that's going to be our top function. And the one that gave us the smaller value, that was this negative x squared plus 2x plus 1. So that's going to be our bottom function. So we just want to identify which curve is which is the top function, which is the bottom function. So once we have that all nice and settled, then we're ready to do the area. So our area calculation is going to be the integral from 1 to 2. And when we set up our formula, it's the top function minus the bottom function. So we want to fill in which is our top function, which is our bottom function. So we'll have our top function first, then minus our bottom function. And just like when we evaluate definite integrals, get the parentheses all set up because we're subtracting here, and usually there's a whole bunch of terms that we don't want to forget distributing that negative to. All right, so our top function we found was this 2x squared minus 4x plus 6. And then our second function was negative x squared plus 2x plus 1. So that was the bottom function. So again, the top function goes first, the bottom function comes second, and we've got our minus sign in the middle. So we've got our integral all nice and set up. So now we could go through and just do the antiderivative, and that's perfectly fine. But there's a lot of redundancy here. There's a lot of similar terms. So usually you want to try to simplify this down as much as possible. It's just going to make everything that much easier. So it's a good idea. Once you get to this point, simplify. All right, so let's simplify our function that we're going to integrate. So we have a 2x squared minus a negative x squared. So that becomes plus. So we end up with 3 copies of x squared. Then we have a minus 4x minus a 2x. So that'll be minus 6x. And then we have plus 6 minus plus 1. So that'll be plus 5. And this is our nice simplified function that we can integrate. So notice we only have 3 terms to integrate here, whereas we have 6 terms to integrate here. So it just makes that much easier if you try to simplify. All right, so now let's integrate. So let's get our antiderivative. So we've got 3x squared here. So the 3 is a constant multiple. Let's make some room for integrating the x squared. So for that, we can just use our regular power rule. So we keep x the same, add 1 to the exponent, take the new exponent, flip it and put it in front. We're done with that one. So now we go on to the next one. We've got our minus 6. Let's make some room for integrating the x term, the single x term. So this is x raised to the power 1. So we're going to write down x, add 1 to the exponent, take that new exponent, flip it, put it in front of the x. And then finally, for that last 5, whenever we have a constant by itself, the constant stays, and then we multiply by our variable. So in this case, x. And then we're going to get ready to evaluate. All right, so before we do the evaluation, again, it's usually helpful to try and simplify. So the 3 times 1/3, simplify. 6 times 1/2, simplify. So when we do that, we end up with x cubed minus 3x squared plus 5x. It's just going to make putting numbers in and just that much easier. All right, so now we're ready to evaluate. And when we do this, just like before, let's get some nice big parentheses all set up with a minus sign in the middle. And when we do this, top number gets plugged in first, and bottom number gets plugged in second, and then we're subtracting. So that's another helpful way to kind of remember, how do you set up this area equation for finding the area? Well, it's the top function minus the bottom function, and that's exactly how we normally do a definite integral. We take the top number, plug it in, take the bottom number, plug it in, and subtract. So it's kind of the same ordering here. All right, so let's get that top number plugged in. 2 cubed is 8. Then negative 3 times 4 is negative 12. And then 2 times 5 is positive 10. And then we go on, we plug our lower number in. So 1 cubed is 1. And negative 3 times 1 squared is negative 3. And then finally, 5 times 1 is 5. So we get plus 5. And it's perfectly fine if you want to leave it like that. But this actually simplifies pretty nice. So the first bit here simplifies to 6. And then we're minusing. And what do we got over here? So we've got 6 minus 3, which is 3. And we end up with 3 as our area. Yeah. So looks good. So that's our area here. And, that seems plausible. Because if we look at the shaded region of this region we were just looking at, well, we've got one unit here, one square unit, another square unit, and then it looks like if we could take this piece and this piece and this piece and merge them all together, that seems reasonable that would be one square unit as well. So the area for this region is 3. All right. So for this example, our two functions didn't intersect. Now, if we go up, that's not always going to be the case. So we might run into a situation like this where we have an intersection point. So our two curves intersect. And that poses an issue because at an intersection point, what can happen? Well, the function that was on top can switch, and it can now become the bottom function. And the function that had been previously on the bottom can now be the top function. So the idea, if our function has an intersection point, is, well, first figure out the x values where that intersection point happens. Then the idea is we're going to break our integration up based on those intersection points. So we're going to look at each of these pieces separately. And then we'll calculate the area for each of those pieces separately, and then add the results together. So in this, we would say find the area for this left region, and then we would find the area for this right-hand region. And to get the total area, we would just add the area from the area from the left side plus the area from the right side. And sometimes you might have more than one intersection point. So, maybe you have 3 regions that you have to calculate the area for. So however many little separate regions you end up with, you calculate the area for each of those individually, and then you add them all together. So I want to practice one example. We're not going to finish it, but I want to just go through how do we find the x values where two functions intersect. So how do we find these intersection points? And let's go to this one. This one's good. So we're just going to start this one and we'll finish it in class. So let's figure out the intersection points. Let's remember. So we can see we've got our two functions plotted here. One of them's a line, one of them's a parabola. And we can see that there are two intersection points. Now you can probably guess just by looking at the graph that one of these intersection points happens when x is -1, and the other intersection point looks like it's going to happen when x is equal to +1. But how do we find these algebraically? So the idea is for two functions to intersect, well, their two y values have to be the same. So we're going to take these two equations and we set them equal to each other. So this is how we find the intersection points. We set the functions equal, and then we solve for x. And usually it takes either factoring or quadratic formula. So that's normally how we do it. All right, so let's get into it. So we're going to take our two functions, x squared plus 2x plus 3, and we're going to set it equal to our other function, 2x plus 4. So we're just taking these two different functions and we're setting them equal to each other. Now this gives us an x equation that we can solve. And the way to solve an equation is try and get everything over to one side of the equation. So right now, we have an x squared over here on the left, and then just some lower stuff on the right. So I'm going to move all this stuff over to the other side. So we'll subtract 2x from both sides, and then we'll subtract 4 from both sides. And when we do that, we're going to have x squared still left over there on the left side. The 2x and the minus 2x cancel. And then we have 3 minus 4, which is negative 1. All right, so this equation, I said normally factoring or quadratic equation, and we're not going to do either here. Actually, this does factor nicely. So this is a difference of perfect squares, so you could factor this. You could also use quadratic formula, but whenever we have x squared and then minus a number, it's easier just to direct solve this. So rather than factoring or quadratic formula, those are very viable. We could use those, perfectly correct. In this case, it's easier just to directly solve for x. So we're going to move that minus 1 over to the other side of the equation. It becomes plus 1. And then we want to get rid of the squared. So the way we get rid of the squared is by doing the square root of both sides. And whenever we apply the square root, so the square root wasn't there to begin with in either of these equations. So whenever we apply it, plus or minus in front. So x is going to be equal to plus or minus the square root of 1, which is just 1. So yeah, we did confirm we have two intersection points, x equal to negative 1 and x equal to positive 1. All right, so this is how you find the intersection points. Take the two functions, set them equal, and that gives you a single equation, and then you can solve for x. So factor, quadratic formula, or sometimes when it's a nice little one like this, just directly solve for x. All right, so we're going to finish this one up in class. So we'll see you then. Bye-bye.